This is the electrochemistry tutorial presented by the SHLTV with reference Cambridge International AS A-Level Chemistry by Laurie Ryan and Roger Norris. So we start with the learning outcomes. So these learning outcomes are going to ask the students who are looking at this video to first pause in order to look at each learning outcome presented by Cambridge International AS A-Level. So So this is the learning outcome. So pause and visualize it. So now let's start. So now you need to know that what redox reactions. We have already seen redox reaction in the introduction of chemistry. So when you have seen the introduction of chemistry with the mole concept, we have seen redox reaction. And these are different redox reaction that you can have. We said that in order for you to balance a redox reaction, we should use the each equation, the half equation of each redox reactions. Example, when you have copper chloride plus iron to produce iron chloride plus copper, so this is a simple one to balance. But usually when you want to balance this type of reactions, the first thing you do is to take iron producing, this one is first this iron to iron, and this one is still iron to iron, this one is iron and this one is iron to iron. In this case you realize that what iron here have converted from iron to produce iron to iron. Since it has converted from iron to produce iron to iron, it has released two electrons, and it has released two electrons now to convert copper to iron to copper. So now this is how to balance the equation. Use the half equation of each part of the equation in order to balance this redox reaction. So let's take this other case. When you have these two half equation, you have chloride ion and chlorine. You see that in this case the chloride ion is going to convert to chlorine with the release of one electron, while the manganate 4 or manganese pentoxide or manganese dioxide. In this case, what do you realize? You realize that binding with this, you have two electrons that is going to be absorbed by manganate. Now, the two electrons which are being absorbed are going to cause the conversion into manganese oxide. So now you balance this side both atomically and charge by atom and charge, and also balance this side both by atom and charge. Since you have balanced all this side, you can now multiply by the numbers of electrons here and multiply by numbers of electrons here. Then you are going to have your answer. So this is how to balance this equation. So now the next thing we need to know that one redox equation. So this redox chapter, the chapter of redox equilibria is divided into two main parts. We have the first part which is involved with electrolysis. The first part is involved with electrolysis, and the second part is involved with electrode potentials. So these are the two main parts in the redox equilibria. In redox equilibria, we have two main parts. We have electrolysis and we have electrode potentials. So now, what is electrolysis? In electrolysis, it refers to the production or extraction of metal and other gases or non-metals from electric interactions. So let's see electrolysis. So here in electrolysis you have different molecules. So electrolysis is the decomposition of a compound into elements by electric circuits. The decomposition of compound into elements by electric circuit is often used to extract metals and other non-metals. This metal cannot be extracted by heating their ores with carbon. So electrolysis is also used to produce non-metals such as chlorine to purify some metals. You have electrolysis is generally carried out in an electrolytic cell. So now let's visualize. So you need to know this is a general diagram for an electrolysis. So now we need to know that we use a battery. We have the positive side of the battery shown by the long arrow, negative side shown by the short arrow. And now in this side we have different electrodes. The electrode that is going to be attached to this positive side is going to be called the anode. The electrode that is going to be attached to the positive side is called the anode, and the electrode that is attached to the negative side is called the cathode. Anode just means that it attracts cations. Anode means that it attracts anions. Anode for anions. Anode means that it attracts anions, while cathode means that it attracts cation. So in this electrolysis, the chloride ion, fluoride ion, hydrogen sulfide ion, sulfate ion are going to move to, or the hydrogen ion are going to move towards the anode, while the sodium ion, potassium ion, calcium ion, magnesium ion are going to move towards the cathode, which is negatively charged. So now these are the different components. After having, we first have the battery, which is going to give the electric current inside the circuit. Then we have the electrodes, where electric current is going to be transferred to the solution. And then lastly, we have the solution occur, which is called the electrolyte. The electrolyte is a compound that is being decomposed. It is either molten ionic compound concentrated aqueous solution. The question is, why is it only these two? We need to know that what, for a solution, for a certain substance to conduct electricity, it must exist in these two forms, either a molten ionic compound, that is a decomposed, that it has been heated and it is molten, or that is molten means melted, or it is in aqueous solution. So these two solutions, or concentrated aqueous solution, these two solutions are capable of conducting electricity. Why? This is because they are capable of conducting electricity because there are free ions in the solution. There are free ions in both compounds. Since there are free ions, these free ions are capable of conducting electricity from one electrode to the other. And then you have the power supply that you have seen, the battery. So now let's see how electrolysis actually occur. We need to know that one. We need to know that when for electrolysis to occur, we have different points to note. So we need to know that when you have a certain compound, here, let's say hydrochloric acid. So let's say that you have an aqueous solution of hydrochloric acid. When you want to solve an equation involved with electrolysis, the first point to do is to identify the ions present in the electrolyte. Example, I've given you a solution made up of aqueous, is a solution of aqueous hydrochloric acid. Aqueous hydrochloric acid is going to be made up of hydrogen ion, is going to be made up of chloride ion, is going to be made up of hydroxide ion. So the hydrogen ion are both coming from water and hydrochloric acid, and the hydroxide ion is only coming from water, with the chloride ion coming from hydrochloric acid. So now these are the different ions present in the solution. So the next thing, when you have given the different ion present in solution, you are going to explain which ion is going to move to which electrode. You say that hydrogen ion is going to move toward the let's say that you want to instead do for aqueous sodium chloride. So you see that there is going to be sodium ion coming from the sodium chloride, and you have hydrogen ion coming from water because it's aqueous, and then chloride ion coming from sodium chloride, and hydroxide ion coming from water. So now when you have this, let's say that you want to do this hydrolysis, what do you realize? You realize that the next point to put is what are the ions that are going to move toward the cathode. The ion that moves toward the cathode, we have two main ions. We have sodium ion and we have hydrogen ion. Both of them are going to move toward the cathode. And then the ion that are going to move toward the anode are going to be chloride ion and are going to be hydroxide ion. So the next point after this is which one is going to be preferentially which one is going to be preferentially which one is going to be preferred between the two, between sodium ion and hydrogen ion, which one is going to be preferentially given a reduced, and which one is going to be preferentially oxidized inside the respective cathodes and anodes. So you need to know that for reduction, you need to know that the reduction and oxidation are going to depend on their level in the electrochemical series. Sodium ion is found higher compared to hydrogen in the electrochemical series. So hydrogen is going to be reduced in preference to sodium ion. Why? In cases of the chloride ion, you see that chloride ion is higher in the electrochemical series compared to hydroxide ion. So the hydroxide ion is going to be reduced in preference to the chloride ion. So those are the points. But now there are different factors that are going to affect electrolysis, like the factor of concentration. If you increase the concentration, if you use now concentrated sodium chloride and not dilute aqueous, you see that now at the level of the anode, chloride ion is going to be lost, because since it is more concentrated in solution, irrespective now of the electrochemical series, chloride ion is going to be oxidized. See, irrespective of the electrochemical series, chloride ion is going to be oxidized to produce chlorine. And now, but at the level of the cathode, the problem here is that the cathode sodium ion is far away from hydrogen in the electrochemical series. So this implies that what, since it is very far away from hydrogen in electrochemical series, it is very difficult to reduce hydrogen with in preference to sodium ion, though the sodium is more concentrated. So it's still hydrogen is going to be reduced at the level of the cathode. And the next thing that is going to affect electrolysis is going to be the type of electrode. So mercury electrode is going to differ electrolysis. We are going to be having differ electrolytic products compared to platinum or other metal electrodes. So these are the points I just wanted to point out in electrolysis. So now let's see the quantitative electrolysis. Quantitative electrolysis is just explanation of how to calculate in electrolysis. Example, you know that charge is given as the current times the time. So this is the charge. So when you have this, you can now calculate. So now we need to know that what in electrolysis you are forming products. You are trying to extract certain metal ores. So example, in this case, when you want to extract, let's say that you extract silver from silver ion, you are going to have 1 mole. Here is 1 mole of silver ion plus 1 mole of current to produce 1 mole of silver metal. This 1 mole of current is actually 1 Faraday. So now let's see a calculation for us to understand this principle. So calculate the mass of lead deposited at the cathode of electrolysis when current is this and through a molten bromide for 20 minutes. So the first thing is to write the reaction. So this is lead 2 ion plus all that. So see that it is 2 moles of electron that is going to produce 1 mole of lead. Since 2 mole of electron producing 1 mole of lead, that 2 mole of electron corresponds to 2 farads. And 2 farads is 2 times 96,500, because 1 farad has been given here as 19,500 coulombs per mole. So the total is going to be 193,000 coulombs per mole. So now when you have this total, you can now come and now say that this is the total quantity of current. So the total quantity of charge that is going to be required to produce 1 mole of lead. Now in this circuit, we have used a current of 1.5 amperes. I have used the time of 20 minutes. So I'll convert this time into seconds, and I'm going to have 20 times 60, and then I'll multiply by 1.5 ampere in order to find the charge. Here I found the charge. I want to find out the charge for this particular reaction. So the charge for this reaction is going to be Q times T, and the total that charge is going to be 1,800 coulombs. Now I'll say that 1,000. Now let's go now and continue. You see that here 19,000 or 190,000 is going to correspond to 1 mole of lead. That is because they're asking you to calculate the mass of lead that is going to be there also. But you need to know that the mass of 1 mole is going to be 207. So 190,000 is going to correspond to 207 grams of lead. Therefore 1,800 coulombs is going to correspond to X grams of lead. Now to calculate that mass of lead, what you are going to do is just to do 1,800 divided by this amount, 193,000 times the mass of lead, and now you are going to have the mass of lead going to find for this particular electrolytic reaction. So this was a brief review on electrolysis. Now let's visualize the other part of redox equilibria, which is electrode potential. So now in electrode potential, we need to know that what there is what is called electropotential. Electropotential is just the electric circuit that one electrolytic plate can produce, the electric current, the electric ability that of one electrolytic plate. So we see a redox equilibria exists between two chemically related species that are different in oxidation state. For example, copper rod placed in contact with solution of ions in equilibrium. So this is an electrode potential. So you need to know that this is a redox equilibria. A redox equilibria is an equilibrium that exists between the oxidized form of an equilibrium that exists between the oxidized and the reduced form of a certain element or a certain species. So this is a redox equilibria. An equilibrium that exists between the oxidized and the reduced form of a species. So this is an redox equilibria, and this is going to produce a particular electrode potential. That electrode potential is going to be the magnitude of the voltage of that redox equilibria. So this is what is called the electrode potential. That voltage of the redox equilibria is going to be called electrode potential, and it is varying for every element. So these are the point to note. So now let's visualize, let's continue with redox equilibria by knowing what is called the standard electrode potential. So you need to know that what the redox equilibria that we have seen initially was the redox equilibria for a half cell, but now it was with no specific values. So now in case of standard electrode potential, we are now going to have reference value from which you are going to do some universal calculation, because we need to know that what electrode potential can vary with respect to the concentration of the ion present there. You have the concentration of the ion, you have the electrode that is being used. So now if we use and we have the atmospheric pressure and temperature. So now if you use the temperature of the medium to be a constant of 25 degrees Celsius or 298 kelvins at a pressure of 1 atmosphere, we use a concentration of solution to be 1 mole per dm cube, and we use an electrode to be platinum. So if we use all this, you are going to have now a standard electrode potential. So what is the standard electrode potential? It is defined as the voltage or the EMF of a half cell. Standard electrode potential is defined as the EMF of a half cell with respect. So standard electrode potential is defined as the EMF of a half cell with respect to a hydrogen electrode, at constant temperature of 1 mole per dm, at constant temperature of 298 Kelvin, concentration of 1 mole per dm cube, and atmospheric pressure of 1 atmosphere. So this is the definition of standard electrode potential. And the question is, why is it that I said with respect of hydrogen electrode? So I said with respect to hydrogen electrode because you are not capable of calculating the standard electrode potential if you don't use a certain reference. We need to know that what voltage is not capable of being calculated if we don't use a reference point. Example, if you want to calculate the voltage between a circuit and something, if you want to calculate the voltage between a charge and if you want to calculate the voltage of a charge, we need to calculate that voltage with respect to something, and what we usually use as a reference point is the earth surface. But now in chemistry, the reference point of all the electric potential is the hydrogen electrode. So now let's see what the hydrogen electrode is going to be made up of. So this is the hydrogen electrode. The hydrogen electrode is made up of a platinum wire inserted with platinum plate. We have platinum wire with platinum plate and platinum rods. So platinum wire with platinum plate and platinum rods, now inserted in a solution of hydrochloric acid, in a solution of hydrogen ion, and that solution of hydrogen ion is going to contain 1 mole per dm cube of hydrogen ion. So this is, and it has an outlet of hydrogen or an inlet of hydrogen here. So that's a hydrogen electrode. So this electrode consists of hydrogen gas at 1 atmosphere, exactly 1 atmosphere, and this is actually corresponding to 1.013 times 10 to the power 5 pascals. So we have hydrogen ion concentration at 1 mole per gm3. We have platinum electrode covered with platinum black. We have platinum electrode covered with platinum black in contact with a hydrogen gas and hydrogen ion. So these are the points to note. This is what makes the hydrogen electrode. So now all these standard electric potentials are going to be calculated from with respect to the hydrogen electrode. And now in order to produce this circuit, we need a copper rod at this position, one electrode at this position. We need the hydrogen electrode, and in order to close this circuit, we are going to use a salt bridge. Usually the salt bridge is either potassium chloride or potassium nitride, depending on the solution that you are going to use. If you have a solution where you have silver, it's preferable to use potassium nitride, because acidified potassium nitride is not going to be soluble inside silver. But now if you have a solution, other solutions, you can use simply potassium chloride. So this is the salt bridge here. So now when you have this salt bridge, so you have now this half cell. So you see that you need to know that the reference point is always hydrogen, and that reference point is giving an electric potential of 0. So copper plus 2 electrons is going to have, you see that it is positive. So it means that we need to know the identification of this positive, the interpretation of this positive and negative on a standard electric potential. When you see positive on the standard electric potential, it means that it's an oxidizing agent. So what do I mean by an oxidizing agent? An oxidizing agent is a species that makes the other species to be oxidized. What's the meaning of oxidation? Oxidation refers to the loss of electron, it refers to the loss of hydrogen, and it refers to the gain of oxygen. So an oxidizing agent is a species that makes the other species to lose electron, to lose hydrogen, or to gain oxygen. Now if you see this positive here, it implies that it's going to be an oxidizing agent. Yeah, you see that copper is absorbing electron, is taking electron from hydrogen. So in this case, the copper is going to convert to copper ion, and the hydrogen is going to enter to produce hydrogen ion. So copper ion is going to convert to copper, and then hydrogen is going to convert to hydrogen ion. That is, this copper is going to move out from solution and then produce more copper rods, while this hydrogen is going to enter to produce more hydrogen ion. So that is what is going to occur in this reaction. So this is the point here. So it's also similar with zinc. With zinc, we instead see that the electric potential is going to be negative 0.76. Since negative 0.76, we imply that negative means that it's going to be a reducing agent. So now what do I mean by that? A reducing agent is a species that makes the other species to be reduced. And what is reduction? Reduction is a gain of electron, the gain of hydrogen, or the loss of oxygen. So what's a reducing agent? Conclusion: a reducing agent is a species that makes the other species to gain electron, to gain hydrogen, or to lose oxygen. You see here that zinc is going to release electrons. So this reaction, what is going to occur? Zinc is going to move in the right hand side, release electron, and makes hydrogen to gain this electron. So zinc is going to move to this side, zinc is going to release electron, and then the electron are going to be gained by hydrogen. So what happens is that the zinc rod is going to enter into solution. This is going to move in the left hand side. Zinc rod is going to enter into solution, release electron, then electrons are going to move through the salt bridge. The electrons are going to come into this side and then react with the hydrogen ion to produce hydrogen, and hydrogen is going to move out into atmosphere. So that is the point that is going to occur in the two different cases. So these are the half cells of non-metals, so for the metals. Now the half cells of non-metal are also having the same constitution as that of the hydrogen electrode, since the non-metals do not have particular rods. As you can see, for the metals you use the zinc rod, you can use the copper rod, you just use the metallic form of those rods for the conduction. But for non-metals, since they are not capable of conducting current, you use platinum wire. As such, use platinum wire coated with platinum black. You place the chloride ion at 1 atmosphere pressure, just like hydrogen ion. So this is 1 atmosphere pressure, and the solution here is 1 mole per dm cube. That is the half cell of non-metals. So now the next one is using the standard electric potential to predict the cell voltage. In order to calculate the electric cell voltage, or the EMF of a cell, in order to calculate EMF of the cell, you are going to do the EMF of the right hand side minus EMF of the left hand side. Let's say that the EMF of this side is going to be having a certain value, like it will take in the case of silver ion and all that, plus 0.8, and we take this one. So it's always the EMF of the right hand side minus the EMF of the left hand side. Usually that's how we do it. But now when you do that EMF of right hand side minus EMF of left hand side, you should always make sure that the EMF should be positive. So this is a point. So now this is how to visualize. So now let's see some weakest. So you need to know that what the more you are positive, the more you are a strong oxidizing agent, and now the more you are negative, the more you are a strong reducing agent. So that's why manganese, which is having an EMF of negative 2.38 volts on a half cell, a standard electric potential, is going to be more reducing compared to zinc, which has a standard electric potential of negative 0.76 volts. And silver ion, which has an electric potential of plus 0.8 volt, is less oxidizing compared to chlorine, which has a standard electric potential of plus 1.36 volts. So this is at the point. So now let's see if it is possible to do a feasibility of reaction, the feasibility of reaction by using standard electrode potential. So now we need to know that there are certain reactions which cannot occur because of standard electrode potential. Let's see the reaction between copper and zinc. We need to know that copper is an oxidizing agent and zinc is a reducing agent, as shown from their standard electric potential. The standard electric potential of copper is plus 33.4 millivolt, and that of zinc is minus 7.6 millivolt. So what happens is that zinc is actually a reducing agent, so it's normally going to release electron for copper to gain that electron, and copper is going to absorb the electron to produce this. So this reaction is going to shift toward the left. So zinc is going to shift toward the left to produce zinc ion and 2 electrons, and then the 2 electrons are going to enter up into copper 2 ion to produce 2 ion and then copper product. So the question is, can a reaction between zinc and copper 2 ion solution occur? The answer is yes, because the zinc is going to enter into that solution to produce zinc ion, and copper is going to move out from that solution to produce copper. But another question is, can a reaction between copper metal occur with zinc 2 sulfate? The answer is no, and this is because copper is not capable of converting from copper here to copper 2 ion and giving electron to zinc, because it has a higher standard electric potential, plus standard electric potential compared to zinc, which is a reducing agent. And this is why here you see that here you use zinc. Here you see that zinc will enter into solution. Here you have copper metal that is going to be produced. What is dark here is copper metal. And now in this case, when you use instead copper and place inside a solution of zinc, you have no reaction. This no reaction is just because of the standard electrode potential. So from here we have visualized everything involved with standard electrode potential. The last thing that I want us to note is, since there is standard electrode potential, there's another thing that I want us to speak about. I want us to speak about the electrode potential as named as such. So electrode potential is it's not standard. It's not standard electro potential. So what is the difference between electro potential and standard electro potential? With standard electro potential, the concentration that you use is 1 mole per dm cube. But with electro potential, the concentration is not obviously 1 mole per dm cube. You can use other concentration. So now, in order for you to calculate the electro potential, you instead use the next equation. Next equation is going to be generally given as what inside the redox equilibria chapter is generally given as RT all over NF, where R is the molar gas constant, T is the temperature in Kelvin, N is a number of charge, and F is a Faraday's constant, which is 96,500 log. So it's RT all over NF ln of concentration of oxidizing agent all over concentration of reducing agent. That's the general formula. But now we need to know that the general formula of this next equation is given as RT all over NF ln of 1 all over Kc. So that's the point. But now in this case, we need to know that the oxidizing agent is usually found on the left hand side and the reducing agent is usually found on the right hand side. That is what the reducing agent solution is usually found on the right hand. So that's why you use this formula. So that's what is written here. So this is the formula that you have in cases of electropotential. So you need to know that the electropotential E is given as the standard electropotential that you have E theta. So if you want to calculate the electropotential, first take the standard electropotential plus RT all over Z. Z is the charge, F is the Coulomb force, R is the molar gas constant, temperature is a temperature in kelvins, F is a is 9,600 and 96,500. And then this is the oxidized form. So it is the oxidized form and is the reduced form. So when you use it. So now example here, you have calculated electropotential of that electro concentration of that. So when you have this, you know that the standard electropotential is going to be plus 3.4 volts. You are going to place it here. We need to know that this, for all this, when you place all the values, it can be converted to 0.095 all over Z log of the concentration of oxidized form. We need to know that between copper 2 ion and copper, the oxidized form is going to be copper 2 ion. So I'm going to place copper 2 ion up, and then I'm going to have plus 0.25 volt. So place oxidized form all over reduced form. But now in a reaction, this is the oxidized form over reduced form. Now in a reaction, you are instead going to say that it's going to be the oxidizing reagent all over the reducing reagent. So we have seen everything involved here with the chapter of redox equilibria. So say thanks for your kind attention. Please don't forget to like and subscribe for the channel. Thank you.